Good afternoon, everybody. Thank you for this invitation. I'm really very happy to be here with you, and especially and in particular, very happy to be able to share interesting science and what I'm doing since at least 22 years here in Trento with my co-national young students. So I hope you will enjoy it. I will be speaking about integrated silicon and quantum photonics, but probably I will spend some slides also to tell you who am I, where I'm coming from, and what I did in these 2022 years in Trento. So I'm currently about 3,000 kilometers far from our home in Trento, in the Fondazione Bruno Kessler, which is in the northern part of Italy. So Fondazione Bruno Kessler is a research institute, but I will talk a bit more about this later on. So as someone already asked me, just to tell you that I studied at the Yerevan State University from 1990 to 1995, and I was in particular in this upper floor of the radiophysics faculty and doing the laboratories in the -1 floor. Then I did my PhD, finishing it in 1999, again in the same place. And then I did some postdoctoral research as a young researcher in the same laboratory. So then in 2002, I moved to the University of Trento, to the Department of Physics, namely where also, you might know, Tatev has done her, let's say, PhD studies and some part of the postdoc. And so I did 4-year postdoctoral research in the nanoscience laboratory. And then I moved to Fondazione Bruno Kessler, which is right behind the road. And I'm there since 2006. So it's about 18 years I'm there. And I changed a bit the topics during my, let's say, research career. During my PhD, I did a lot of theoretical work, partially also because of the fact that experimental work was very difficult to do in those years. Then I worked a lot on a material that is called porous silicon. I don't know, probably you have heard. Let's say, fashion about this material is already gone, but that was very, very, let's say, boom and hot topic in those years. Then I moved to University of Trento, where they were working with porous silicon, and I started to do experimental work. And I realized that I was probably more an experimentalist than a theoretician. So everything went very well. It was very productive 4 years, and maybe it will be worth if I show you with a couple of slides some activities I did in University of Trento before moving to Fondazione Bruno Kessler. So the main topic I was working on was about the so-called optical superlattices, and these are so-called coupled microcavity structures. But for those who are not familiar, I will try to present a couple of, let's say, basic concepts. And maybe for many of you that are, let's say, have more experience with solid state physics, you will be finding easily the analogies. So suppose we have a single quantum well. So you have a quantum, you have a potential well, and on both sides it has, let's say, potential barriers. So what happens? You have different states of the quantum particle. For example, the ground state is described by its wave function, and the state has a certain energy. So in the optics world, the concept which describes or the analogy of the optical world for this, the counterpart is a microcavity structure. In this case, we are speaking about one-dimensional optical microcavities. So you have layered structures, and you practically look at the light propagation properties in the direction vertical to the films. And a microcavity is essentially built by two mirrors, which are sandwiching resonant to the particles energy or waves energy, a resonant cavity. So if you look at the transmission spectrum of a single microcavity, you will see that there is a large spectral region where, let's say, the photon propagation is prohibited. So it is the analogy of an electronic band gap, okay? And the cavity is actually a defect, and this defect allows to have a very, let's say, a sharp resonance transmission at a given wavelength, and it's a gap state. So it's the microcavity transmission line. So it is essentially a filter. So it rejects a lot of wavelengths around and lets pass only a given wavelength. So this is the analogy of a single quantum well from the solid state physics. Now what happens when you put two identical quantum wells close to each other, where saying close means that the potential barrier between two quantum wells is thin enough to allow, let's say, a crosstalk or an overlap of the wave functions of the single wells. So in this situation, what happens that since they are identical, the quantum wells, so you have degeneracy, and they share the same energy for all the levels. And in particular, the ground state split into two states, let's say the symmetric and antisymmetric states. So what is happening? You have now a wave function which is spreading over two quantum wells. So you cannot look at a single quantum well separately. So it has a strong connection to the other one, and this is a unique system now. And in optical, so now suppose if you put many identical cavities with identical barriers between them, so you will have n quantum wells that are coupled to each other, and the single unique state of the ground state will split into exactly n splitted, let's say, states, and they are called electronic minibands. So the analogy in the photonics world is that when you put several identical microcavity structures, like I showed you before, one after the other, this way you will create a photonic miniband. So what will happen that your single state, the microcavity state that is responsible for one single cavity, isolated cavity, will split into n states around the central wavelength. And this will create a miniband of gap states. So I hope with this you can draw the parallel between the photonic world and the quantum or solid state world. And the main reason for this is that these different systems, they are all how to say, they are described by waves, and in two different cases the waves are different waves, but eventually it's all treating with wave theory, and you can find the analogies both in the electronic side and also in the optical photonic side. And in the University of Trento, I started to work, knowing, let's say, from my PhD course studies, more about the theory of porous silicon. Then I started to build these coupled microcavity structures, which you can see in this scanning electron microscope image. You can see the dark identical lines that are lambda half cavities. And then you have these mirrors in between each cavity. So this is a microcavity, coupled microcavity structure. Now, the question you might ask is why, of course. And so I was working on a project, a collaboration project between different Italian groups. And project was aiming in studying different analogies between the electronic world and the optical waves in dielectric structures. So these analogies are really very, very sound, and they are formally described by the same equations. And then knowing that in ordered dielectric systems, periodic dielectric systems, you can realize the analogy of an electronic crystal by realizing photonic crystals, we thought that they can exhibit very similar properties to electronic solid state materials. And then the interest was to study some, let's say, famous phenomena coming from the solid state physics and try to, let's say, figure out if they are observable also in the optical or photonic domain. So, as I said, there is a wide spectrum of wave phenomena, and the interference of waves is really crucial for these. And we started to study how the light interacts with the matter, which is, let's say, in purpose built to create interference between the layers of dielectrics. So the first famous phenomenon that we were studying were the electronic Bloch oscillations. And the electronic Bloch oscillations were predicted in 1929 by German physicist Felix Bloch. So the idea was the following. So imagine a solid material which has band gaps and has a loud band of states where the electron can travel through the crystal, staying always in the same Brillouin zone. I just want to ask you if these things are familiar with you or they are totally new. But I suppose as you have been physics department students, or you are, you should already have known about these things. So then I continue. Otherwise, you just stop me and ask questions, please. Now, what happens when you apply an electric field onto a crystal? Now, you know that the electric field is adding a potential, which is variable with the space. And then this leads to kind of tilting of electronic bands. And so all the allowed bands and the band gap edges are tilted. Now, if you insert a particle, a quantum particle, into the band gap, which is within space at some point is, let's say, closed by the edges of the band gap, so this particle will start to oscillate in space. But this oscillation is then also an oscillation in the quasi-impulse, quasi-vector space. So if you are familiar with what is the Brillouin zone, you know that this is the, let's say, available wave vectors for an electron, for a quantum particle, which can be covered and they are not repeated within the Brillouin zone. When you go out from this zone, it is something equivalent to this zone. Okay, so all what is happening within a Brillouin zone, you can study and apply to your, let's say, wave function equations. So now, if you look at this graph, I have a small animation that is showing. Now, when you have an electric field applied, this electric field is transferring energy to the particle, and the particle starts to move within the Brillouin zone. So it moves in the Brillouin zone, first accelerating and then decelerating, okay? And when it reaches the edge of the Brillouin zone, it immediately appears on the other side, okay? So let me see, I will try to show it another time. So when it appears at the edge of the Brillouin zone, it is equivalent, so it can, instead of going out, it will appear here, so it's the equivalent. So then what happens that your particle is performing one period of oscillation. And this period of oscillation is the Bloch oscillation period, and is given by the electric field, its charge, the Planck constant, and the crystal size, okay, which is expressed as a reciprocal space vector for the quasi-impulse. Now, the idea was really very bright, and but Bloch was understanding that in order to experimentally observe this phenomenon, the situation of experimental physics in those times could not allow the experimental verification. Is because the electron wave packet is, since they are charged particles, they are losing the coherence with time. And the Bloch oscillation period calculated for a crystal, which has a very small crystal lattice. This means very tiny d means very large Bloch oscillation time. This means that in a very large Bloch oscillation times, you lose all the coherence of your wave packet, and you can no more observe the oscillation of a wave packet, even one. So this idea remained as a theory for many, many decades, and only with the advent of electronic superlattices by Ezaki and Tsu in IBM research, when they first time realized, I suppose, with molecular beam epitaxy or epitaxial methods, they coupled quantum well structures, which have a larger periodicity. And this means with large periodicity period, you have shorter Bloch oscillation times. And only then, even after 20 years of that, let's say, system invention, was the first time that people observed electronic Bloch oscillations in electronic superlattice structures, in coupled quantum well structures. So eventually the ideas of Bloch were confirmed for electronic structures, and people were happy with that. So what we were thinking, to try to see this wave phenomenon in an optical counterpart. So, photons are not charged particles, so you cannot apply, if you apply an electric field, the photonic bands will not tilt. But there is a trick in optics, and this trick is applying a gradient of the optical path of the layers through the structure. So it means that every time you repeat a structure, like the brown one, you change its thickness or its refractive index by a very tiny amount, and this will allow to create a gradient through the structure. Of course, this gradient is, once you make a structure, is fixed, and you cannot change the bands as you wish, but it will provide a tilted situation of your photonic bands. And when you tilt your photonic band structure by a gradient, what happens that the mini band states that you saw in the spectrum a couple of slides before, that mini band spectrum transforms into equidistant states of photonic states, which are called Wannier-Stark ladders. So they are equidistant in energy. Okay, and to cut it briefly, we did experiments, and we observed optical Bloch oscillations, optical Bloch oscillations with mimicking the tilting of the bands at different gradients, so different samples. But we clearly saw that the period of the oscillation was changing, and we were doing time-resolved spectroscopy and injecting a light pulse, which is the first one. Let's say you see the reference one. And then we were detecting the output of the structure after some time, and we were observing in time oscillatory output of the signal. So this was published in physical review letters. We were very happy because we went onto the cover of the journal also, and big satisfaction. So in the next step, sorry
for interrupting. Can I ask a question in your last slide? So this is not really mirrors. It's like two different transparent materials that connected with them, very small thicknesses that have. and the law period defined by that materials. Yes, or I don't understand correctly.
Okay, no. Let me go a couple of slides back. Should go. Okay. Okay. So can you see the mini band? So
Yes.
the story is the following: this wavelength, where you have a resonant for a single microcavity, is defined by the optical thickness of this layer, which is the refractive index of this central layer times its thickness divided by 2. This creates a constructive interference of the plane wave when it reaches here. While the mirrors, so they are not metallic mirrors, it's not a metal mirror, it's not a single layer, it's the so-called Bragg mirror. So you have the Bragg condition. So when you create sequence of, let's say, two materials with two refractive indexes that are, let's say, N1 and N2, and you build their thicknesses in a way that N1 times D1, so its thickness, its optical thickness, is lambda 4, and the other one, N2, with its thickness D2, is again lambda 4. So they are all quarter wave. So they are like quarter wave plates. Okay. When you put one after the other, you create a mirror. And if you do not have this cavity, only this mirror, you will see the same spectrum without this transmission. So you will have a mirror that does not transmit anything, because this is transmission, at this wavelength, okay, around the lambda. So this is a Bragg mirror. Now, when the Bragg mirror is not 100% transparent, 100% reflective, you have the wave function, like this wave function, that is spreading somehow into the mirror. Okay, so it's centered in this cavity, but it's spreading in. Also, the other one has a wave function, the same wave function that somehow spreads or penetrates into the mirror. When this mirror is not ideal, so these two cavities start to communicate, let's say. So they couple exactly like here. Because of this coupling, or the strength of the coupling, they are the single resonance, which is common for both, is splitting into two resonances. If you put like 7 resonances, 7 cavities, your single resonance, which is equal for all of them, you will see a spectrum of 7 separate peaks. Okay, I don't know if I was clear or not.
Okay, I understand. So one more question from God. Yes.
Yes, thank you very much. So my question is connected to the reverse engineering of the system. So in this case, we have a complex system of microcavities, mirrors, and so on and so forth. And then, as you mentioned, you do time frequency analysis to get the existing modes, right? So, but the question is, how do we do the reverse engineering? For example, we choose a mode, and are we able to construct the following system? I mean, first we choose the mode, then we build the complex system of microcavities and mirrors to get that mode.
If I understand correctly, so in this case, you have only one allowed mode of transmission. If you make your cavity optically thick, like n times d, is exactly lambda half. If you have lambda half, if this size equals to a lambda half, you will have only one mode. So it's like a single mode waveguide. But this is not a waveguide, it's planar structure, okay? Mm-hmm. So you have one mode, and if you want to engineer at a given wavelength, you have to know which material are you using for the cavity. So you have to know the refractive index of this material at the wavelength of your interest. Mm-hmm. You have to make the thickness of this layer d such that the d is equal to lambda divided 2 times n. Okay, so this way you assure that when you make the mirrors around, you will get a resonance at wavelength lambda.
Yeah, I totally get it. But the question was, do we just need to change the width of cavities? Or do
In
we
this
need
case,
to
for Bloch
also
oscillations,
think about their distributions and their
no,
distances
okay.
between from mirrors and yeah.
No, so okay, now I understand. The gradient we apply is the same gradient over all the structures. So also the cavities are slightly, let's say, different in this case. Otherwise, you would not get a Vannier-Stark ladder. So you will not hit the band. You see this image. So you see all these horizontal lines are the energies of the different cavities, and they are at different positions inside the sample. So the last cavity is quite different from the first cavity, but having a tiny gradient between each other makes them couple everything. So this is the concept. So the gradient is applied on all dark brown layers, on all mirror constituent yellowish layers, and also on all the cavities. So they have all the same gradient.
Oh, okay.
So this you tilt everything, let's say, kind of linearly. Otherwise, you will get a very crazy form of the bands, and which is not a good idea, let's say.
Oh, okay. Okay, thank you very much.
Okay, maybe if we have time in the end, I would be happy to answer more questions. So, because since I'm probably running out of time and I'm still telling you what I did before doing integrated photonics, because these were one-dimensional structures, but I think it would be nice for you to know a bit the different research we did here in past. So then the next natural idea we had right after publishing the Bloch oscillations was the Landau-Zener tunneling. You know, in past when there was the Soviet Union and the West, so the scientists were not communicating too much, and they realized at some point that many ideas were independently, let's say, put forward both by Western scientists, European or United States scientists, and also by Soviet scientists. So this is something probably you have heard also about many other phenomena, like also Gauss-Ostragradsky's theorem or whatever other thing. Also the Landau-Zener tunneling is something very old, independently studied by Clarence Zener, and in Bristol, and also by Landau, Lev Landau in, I don't remember, in Moscow, I suppose. In 1934, they both suggested this idea that if you have a solid which has several band gaps, and you tilt enough with an electric field these solid materials bands, it can happen that a particle from one band, without gaining extra energy, so without going up in energy, it can simply tunnel through the very thin band gap between two bands. So this is the tunneling, so it's a Zener tunneling called. And in a particular case, for, let's say, finite number of states, you can have the so-called resonant Zener tunneling, which means that the particle in principle can be tunneling through the band gap. But if on the other side you don't have exactly the same allowed state, it will not be able to go anywhere. But for a certain tilt, you can have two states in two different bands that are in energy aligned perfectly, and then the particle will tunnel from one to the other. And this is called the Zener tunneling. So this is somehow a bit more complicated situation of the, let's say, Bloch oscillation. And we decided to think of realizing also a similar structure in photonic coupled microcavities. So we designed if I can be immodest, I designed, because this was my idea totally, and I designed two types of cavities like C and D, with the similar mirrors coupled between each other. So then every C is coupling to another C, okay, and this way around. And all the cavities D are coupling between each other. So they have different thicknesses around a given wavelength. They are tuned, for example, for their thicknesses to be slightly longer wavelength around lambda and slightly lower wavelength around lambda. So this actually creates two mini bands of states. And in the transmission spectrum of this kind of structure, you will see, instead of one single mini band, you will see two mini bands, and they are separated by a small mini gap. And then clearly you understand the idea is to apply a gradient and to tilt these two bands, and at some point to see a very sharp transmission occurring in the center of what is originally a rejection band, so a band gap. So we did, so this is just to trace the, let's say, edges of the bands. We did, so these are simulations, but we did, of course, experimentally with a gradient, applied the same gradient all over the layers. We got, let's say, tilted bands, but these tilted bands are not enough. So you can, as you see, there is not a state that is on the other side exactly aligned in energy with the other. So this one, we would like to couple to this, but you need to tilt it more. So you see still there is zero transmission here. But for a given and correct tilting of bands, you will see that the last state of the first mini band and the first state of the other mini band, they coincide in energy, and then you get a very sharp resonant tunneling. So if you inject light here, it would very easily and with a high transmission go through your structure, even if your structure is kind of 100 layers thick. Okay. Now we did it also experimentally, and you can see these are spectrum of the mini bands. They get almost zero, but at some point of gradient, you get this sharp peak. And I remember this day, and I will remember all my life because it was a very, very exciting moment. And while I was alone in the laboratory, so then we did it much more fine tuning of this experiment. And we were able to publish another physical review letters, and we're very happy. Then this research continued. We did some other things. We used, since this material, porous silicon is porous, you can also drive vapors inside the pores through the structure, and the vapor is condensing in the nanometric pores. And by condensation, you change the refractive index of the material. And by changing the refractive index kind of dynamically, because you can inject vapors, you can warm it up and release the vapor, you can dynamically tilt the bands. And the Zener tunneling, we did also dynamical tuning, like in this paper. Later on, I will share the slides with you. So if you are interested, you can have a look on papers, or I can send you the PDFs, which is much easier. And then we published also a Nature Photonics paper on optical switching with capillary condensation. Yeah, this was also very nice piece of, let's say, series of research on Zener tunneling. Okay, the last thing I would like to show my studies about these periodic or disordered one-dimensional crystals is that there is another idea, which is having the name of the very famous researcher Philip Anderson, which is probably one of the most cited physicists in the world. And in 1958, he published a paper which was actually saying that if you have a perfect electronic crystal and you start to dope it with impurities like ions of other materials, the doped crystal can become so much disordered, its electronic states, that you can totally stop the diffusion of electron waves. Okay, so it kind of from a conductor you get an insulator, so it's kind of so-called Mott transition. So but then in late 80s, two researchers Sir John Pendry from Imperial College, and also Alexander Tartakovsky from Moscow State University, I suppose. They did independently this, let's say, their idea that often it was noticed that in very extremely disordered structures where you suppose that the current cannot flow, sometimes at some electric fields you have very sharp electric current of transmission. And the idea was that very occasionally and extremely rarely, exponentially rarely, you can have that two electronic states, because of this very disordered structure, can very occasionally get the same energy, and they can be kind of resonantly coupled. And for that energy, you can have a very sharp transmission or transmission for the waves, or electric current burst through a disordered electronic crystal. And this was also theoretically set there. And then we did also a random sequence of lambda 4 layers. So they were no more periodic, and we totally randomized them. And making different thickness of the layers, we noticed that the transmission is exponentially dropping as the sample size increases, as it is predicted by the theory of Anderson localization. For the light, it is also obvious, because these are waves. And then we noticed also that at certain frequencies, occasionally we could get very high transmission. So instead of like almost zero transmission, for a very thick sample, you get almost one transmission. And this was also explained because of the formation, very occasional, let's say, setting of several identical cavities within a random structure. So this is, you have to remember that this is a random structure, so you do not design coupled microcavities. You design a series of random structures, but at some point, the strange cavities are formed, and you cannot predict their formation, but you can get a resonant state between different necklaces. So they call necklace states because the wave functions are coupling like this, and they form kind of necklace. We did several other publications about this. Yeah, and then, okay, and then now I'm ready to speak a bit about integrated photonics. If you have no specific questions, I can continue. Should I, or there are questions?
There is one question. Yes, go.
Okay.
Yeah, I have a question. So the first one is connected to the Landau-Zener slide that was 13th, if I'm not mistaken. Yeah, this one. So the question is about the polarization. So I assume the light is polarized, right?
Yes.
So when it comes to the system of microcavities.
Yes, it's a very good question. As I said, these are one-dimensional structures. So they are like pieces of paper, one over the other. Okay, so it's one-dimensional. And the experiments typically were designed for normal incidence. Okay, so you have plane wave that is impinging on your let's say plane of the layers, and unless you are not out of normal incidence, the polarization does not matter. You get the same identical spectrum. Okay, as soon as you tilt your structure, so you send the light, let's say not normal to the plane of the layer, so these are the layers. So if you go vertical, so whatever is your polarization, the transmission is the same, because the P and S polarizations are not split. But when you go incident, let's say out of normal, you will immediately see that you get two spectra for two different polarizations, and this is normal. And instead of complicating our life, we always did the normal polarization incidence. Of course, if you go out of plane, you will get all the spectrum messy, and the spectrum will shift towards the shorter wavelengths. And eventually you can even get, for example, Zener tunneling with flat bands, but with tilted polarization, let's say, incidence. But that's much more complicated. So in one word, to respond to the question, yes, it is, this structure is sensitive to the polarization if your incidence is not normal. If your plane wave is parallel to the layer structure, you will get identical spectra for whatever polarization. And we were doing in vertical configuration, this experiment. Is it the answer to your question?
Yeah, it pretty much answers the question, but so there is a follow-up one, if I may.
Mm-hmm.
Yeah, so you already mentioned that the dimensionality of the system is 1. So
yeah.
So what would happen, let's say, to the solution if the dimensionality was 2? So let's say the microcavities are spread in a plane, not directly one after the other one. And if the polarization of light will decide something, how would it be? So
yes, this is also a very nice question. Let's say the first thing I can think of 2D is to work with, let's say, waveguiding structures. For example, a waveguide, and in the waveguide, you through the length of the waveguide, you like cut or create different pieces of these layers. Okay, so if this is a two-dimensional, most probably you will have two different behaviors for the, let's say, transverse electric and transverse magnetic fields. Technically, it would be extremely difficult to experimentally, I mean, to realize a very good quality structure, which is something like over 50 layers thick. But in principle, you would see the same behaviors, and probably you will get two different types of mini-bands for one polarization and the other. Because in normal waveguides, unless it is not a square waveguide and it is, and the polarizations, transverse electric, transverse magnetic, they are not degenerate, they have different, let's say, effective refractive indices, you will get different cavities. So there, instead of the material refractive index, so that instead of using the bulk index of the material, you have to consider the effective index of the mode. Okay.
okay. Okay, thank you.
Yeah, these are things we can talk a lot about this. We never even thought to realize in 2 dimensions. Also because, to be honest, so this research can be bright research, if you want, for very scientific scopes. But if you want to do practical things, they are not really practical. Yeah, and with very many number of layers or sequences, it is very difficult to realize, for example, in an integrated waveguide, these kind of structures. For example, instead of that, you can use coupling of ring resonators. This is much easier, but typically the ring resonators are not single mode cavities. So then for every resonance of the ring resonator, I suppose you are familiar with those, you will get bunches of mini-bands. Every resonance of your resonator will be split if you couple many rings, for example. And these are typically called crow structures, coupled resonator optical waveguides. And they are much more, let's say, practical and yeah. But I don't think that Zener tunneling has been ever thought to demonstrate on those.
Okay.
Okay.
Yeah, but so in these type of setups, we are just interested in one mode, right? So
yeah,
we just take one mode and do the rest. So, okay.
Yeah, in what I was showing, you are interested in one mode, especially because these are one mode cavities. And then you can have two different polarizations if you tilt the angle. But if you think of two-dimensional ones, you should also consider the different polarizations. And maybe if you have, for example, Zener tunneling working for one polarization, it is not said that it will work for the other polarization.
Yeah.
Or you will get a mix of polarizations and the picture will be even more complicated to, like it will be an overlap of two polarization transmissions.
Oh, okay.
Okay.
Yeah. Okay, thank you.
So maybe I continue. So we are now, okay, so we are now here. Can you tell me how much time I have? Because I know that I'm talking really a lot. It's already 1 hour done.
You have time. You have time.
Okay, I'm okay with my time. So just tell me when I have to accelerate. So now, right now I'm sitting somewhere in this floor, yeah, behind the windows, on the other side of the building. So this is where I'm currently working. This is the Fondazione Bruno Kessler. And the University of Trento is right on the other side. So this is a Trento University building. And all this stuff is Bruno Kessler Foundation. And yeah, this is a non-profit public research institute. It's a research and technology institute. We have several centers. I will these numbers. Okay, several laboratories. We have micro nanofabrication laboratories, so the clean room facilities, and the center hosts more than 450 researchers. And there are different centers. The two main centers that are situated in this area are the information and science technologies. So they are practically programmers and artificial intelligence related research. And then the other center where I am working is the Center of Sensors and Devices. And we are more, let's say, experimental oriented research center. So the Sensor and Devices Center, as I said, we work also in the clean room, a lot of activity in a clean room facility. We work on 6-inch silicon wafers. So we use technologies to create highly integrated sensors and devices. And among them, we have the integrated classical and quantum photonic devices, the fabrication of those and characterization, design, and whatever. And the group where I work is called Integrated Photonics Group. And yeah, we have several PhD students, postdocs, researchers, senior researchers, the head of the unit, Georg Pucker, and we have also some technicians. And yeah, I will not read line by line all this stuff, but in principle, the application field of our circuits is telecommunications, quantum photonics, miniaturization of spectrometers and interferometers and sensing and things related to all of this. So since several years, we are pushing hard on the quantum integrated photonics side and trying to bring onto a single chip all the different functionalities of a quantum photonic device that in principle one would like to have. So essentially these are the single photon sources, the integrated circuits to perform quantum interference architectures, and then eventually detectors of single photons. Now, so the technology we use here is mainly, let's say, silicon technology, but saying silicon does not mean that we work totally only with silicon. Of course, the materials that we use are crystalline silicon and, let's say, the family of silicon-related materials like silicon nitride, silicon oxynitride, and these are different technologies, but they are all very friendly to the CMOS-like complementary metal oxide semiconductor technology of silicon. So you cannot, for example, process here materials that are, let's say, enemies of silicon, for example, gold or other metals that easily go into silicon and they create impurities. They are not good, especially who is creating electrical devices. But for the materials that are useful for integrated circuits, we mainly work with silicon nitride and oxynitride in the spectral range over 400 nanometers of wavelength up to 2-3 microns in several cases. And with silicon, we typically work at around the telecom wavelength, 1.55 micron, and we cannot go down shorter wavelengths than 1.1 micron, because then the optical band gap of silicon starts to prevail and it absorbs whatever light is visible or very near infrared light here. Instead, silicon, in these cases, we use silicon nitride materials, and silicon, if possible, we use as a photodetector material. So the photons that are transmitted without losses in silicon nitride or oxynitride materials, and they then can be sent into the silicon substrate to be absorbed and to generate photocurrent, so photodetection. So one briefly remembering that in quantum mechanics and electrodynamics, there are similar things, and this I could say even many slides before, but now here is the another time of the place to say that when you have a quantum well and your wave functions are localized, or they prefer to sit where the potential is low. In the photonics case, the light waves tend to deviate or to, let's say, concentrate in the part of the material where the dielectric function is higher. So when you create this is a cross section, create a waveguide, so a material that is guiding the wave, the guiding material has a higher index, while all the rest that is around your waveguide is a lower index. So it confines the light within this, let's say, geometry, and the light can propagate many far distances owing to total internal reflection. So the guiding components we deal with can be of different types. The planar waveguide, so this is essentially injecting light in this plane. It will be confined from top and bottom, but this is not a very smart idea, because in plane you don't have any confinement, and your beam after some microns of propagation will diverge and you will lose all the mode. The useful thing is to use channel waveguides. They are waveguides that have a cross section of a rectangle. It can be a square also. Or there is another option to create a waveguiding material, which is called the rib waveguide or rib loaded. Then another similar to the rib loaded one is the strip loaded, that uses a loading material which has an intermediate refractive index between the let's say insulating or cladding layers and the guiding layer. I suppose many of you are already very well familiar with waveguiding, so I will not explain basic ideas here. Just to say that in our technology we can go for one-dimensional structures. So like the questions you were asking before. So like, for example, the multi-layers I was realizing in the University of Trento with porous silicon. Here we can do a single layer depositions, but to make many, many layers, it's very costly, and then it can cause unwanted stress of materials, because these technologies are typically using high temperature depositions, and the stress accumulated is very high. But then for guiding in the plane, you use waveguides. As I said, you have a mode, you have two different polarizations. transverse electric and transverse magnetic, they can propagate. And then we can even realize, let's say, several levels of wave guiding structures, call it 2.5 dimensional wave guiding structures. Okay, so this is a bit technical. Well, this part of the presentation will show you more technical things rather than very interesting and exciting science. But at some point, you know, the knowledge has to be put into a more repeatable technology and try to make out something useful out of that, okay? And this kind of technologies allow to build many chips from each wafer, and you can get 200, 300 chips identical from a wafer with a single fabrication run. So we have different types of substrates that we use. As you can see, we always work with silicon substrates. So this is a cross-section. This is a silicon wafer cross-section. It is something like 600, 700 micrometers thick. And then we have different technologies with thermal oxide grown on top of silicon, and then we build photonics on top. Or we can use silicon substrates with epitaxial silicon film, which is a necessary film, very low doped silicon, where you can create PN junctions and also create photodetecting devices. And then there is the so-called SOI technology, silicon on insulator, where you, with this type of wafers, you buy and you create integrated circuits in the top layer, in the device layer of the crystalline, very thin crystalline silicon. So this layer can be 1 micron thick, or 500 nanometers, or 220. Okay, so the idea of building integrated chips is just to squeeze, especially in the photonics, integrated photonics concept is to squeeze an optical laboratory into a very tiny chip. So this is actually possible, and we are not the only ones that do this. There are many places in the world where integrated photonics is developing, and there are much, let's say, important players in the world. But I will talk about our things, because we have some special things that others do not have, and this, in many cases, can give you advantage. So, so you see an optical laboratory with free laser beam. You have pinholes, you have mirrors, you have beam splitters, you have detectors, and this is a very large optical laboratory. And probably Tatev also remembers still this laboratory. This is the LUMI2 in the University of Trento, where I was working also years ago. But then all these concepts you want to bring down into a chip. It is clear that to do so, you have to transfer the concepts from free space optics into integrated optics devices. So the concepts are in almost all cases possible to transfer. This is an optical image of a, let's say, racetrack resonator with 2 coupled waveguides for putting in the light and extracting light out from this long racetrack. And for comparison, you can see the dimensions with respect to the diameter of a typical hair of a person. So all these things are really possible to do, and for this you use optical lithography and pattern etching and transferring technology. And yeah, now there are several components on this picture, and I put this image just in purpose to show you that from the world of the free space optics, for example, beam splitter and normal beam splitter, you can use, let's say, coupling of 2 waveguides. So the light that comes here over a certain distance, it can partially be transferred in this arm and partially can go ahead. So it's called a integrated beam splitter. So it's a coupler, okay, optical coupler between 2 waveguides. And the amount of light you want to transfer from one to the other can be controlled by calculating and defining the length of these two parallel waveguides. And eventually, you can also have a fixed coupler, but in many cases that I will show you in later slides, you can have thermo-optical tuning of the refractive indices of these materials, which can change the coupling and then which can change or modify the amount of the transfer of the light from one to the other. And these structures are typically called phase shifters, because you shift the phase of the coupled modes, and because of this they transfer in one way or the other. And then the optical fibers are clearly what are in integrated photonics called waveguides. Okay, so the waveguide coupler is the beam splitter, and the waveguide is the optical fiber. Okay, so it is possible to create many integrated different devices for nonlinear frequency generation. You can generate them in a ring resonator. You see this brown or reddish part, which is on top of the waveguide. This is a phase shifter. It is hitting the resonator just to shift the resonances of your ring resonator or to modify the coupling. You can use these rings also for passive routing and filtering of signals. You can use waveguides and coupled ring resonator structures, like as I was saying before, crow structures for different applications in quantum photonics. You can generate entangled and heralded photons. You can perform quantum quantum interferometry with signals. You can create interferometers instead of a monochromator or interferometer, free space one. You can everything define onto a chip and work with tiny waveguides. Now, finally, I will move to the main topic of this talk, and I will talk about the project EPIQUS. So it's a Horizon 2020 project, FET project, and EPIQUS stands for Electronic-Photonic Integrated Quantum Simulator Platform. So the project was for 4 years, and it finished right on the 30th of September of 2024, but it was extremely successful for us. We did a lot of important developments, and we are continuing this research. And shortly, I will show you with a very general concepts what was this about. So we had several partners in the project, and it is coordinated by Fondazione Bruno Kessler. And nearby, we have the partner of the University of Trento. We have quantum photonics and algorithms experts from Bilbao, Basque Country in Spain. From Vienna, we have two groups: the University of Vienna for quantum optics, the Technical University of Vienna for electronic control devices, and you will see now why it was needed. Then from Germany, we had the group of Rostock University. They are quantum optics specialists. And then we had a non-European partner from South Korea, from Pukyong National University, and they were experts in creating quantum algorithms and controlling through softwares and algorithms the hardware that we fabricate and develop. Okay, so I will go through. So the idea was to create a quantum simulator, but very fast to say what is a quantum simulator is that you can use the integrated photonics to build and realize miniaturized versions of optical quantum circuits, like optical tables, which are full of hundreds of mirrors, splitters, as you saw in the picture a couple of slides before. And you can miniaturize, first of all, everything. And then you can use the integrated quantum photonics for applications in quantum computing, quantum communication, quantum simulation, or generating quantum walks or metrology. Now, the scope of EPIQUS is more related to realizing a quantum simulator. So it is intended to simulate a system of interest. They can be different systems. Typically, these are systems where many body interactions are taking place. And a classical computer cannot easily calculate the outcome or the, let's say, Hamiltonian or the scenario of development of the system. And instead of that, if you find a system, in this particular case, a photonic integrated system, which can be designed in a way that the Hamiltonian that describes your photonic system is formally the same as the one that describes your system, you can run experiments with single photons. For example, you have many body interaction of like 10 electrons, and you write your equations, and for these 10 electrons you have a Hamiltonian, and then you build a photonic integrated circuit, a network of waveguides, beam splitters, Mach-Zehnder interferometers, and so on, for 10 input single photons. And then you run the propagation, you propagate these photons into this circuit, they interfere, excuse me, and they go to the output of your network, and then you get a statistical result, which will be the statistical result of your experiment that you would like to do in the real life. So it's like having a flight simulator. No, you build. You want to imagine what will happen with a very new superjet, but instead of flying on it for the first time, when you are not sure, you go into a room with a flight simulator and you simulate the real scenario. So in this sense, the quantum simulator is a machine that, or a system that is simulating a real problem, and this its output is statistically the most expected output of the system of real interest. It can be a quantum chemical reaction or study of the high temperature superconductor materials, or many body interactions from solid state physics. Now, in the EPIQUS project, the aim was to demonstrate a cheap, easy to use quantum simulator device, which is capable to simulate several quantum mechanical problems. So it's a proof of concept eventually, just to show that it is possible to realize in a compact device, but what is more important, that operates in ambient temperatures. Because you might know that in quantum optic experiments, in many cases, in almost all cases, the part of the detection has to be done at cryogenic temperatures, because you have less noise, you have less electronic noise, you have superconducting detectors, and they are extremely efficient at several Kelvin's temperatures. But the idea here is to use silicon-based single photon detectors, SPAD devices, and to work, because they work at room temperature and they work pretty well. So the system of the EPIQUS is built in by two levels. One is the software level and the other one is the hardware level. So the software level is what you see here. I will show you in the next slide. So it's a level where a user starts from a computer, and using quantum programming languages, he can write through a HTML code the quantum problem or the sequence of quantum gates he would like, he or she would like. And then this is transferred then to the hardware. And in the hardware, after several, let's say, commands and signals, experiment is running. And then the result of the experiment is read out back to the computer. It is sent to the user and is plotted the result of the, let's say, quantum simulation as a histogram or whatever is the need of the user. Okay, so the user writes a program, it's sent into the HTML code. The HTML code transfers into primitives, and these primitives, okay, from here, they are transformed into commands to an electronic processor, which is called FPGA. You send signals. Essentially, these become numbers of currents, signal currents that the processor sends to your device. And it sets your device to a certain condition. You will see later on a bit more clearer what is happening. And then the system runs experiments. Single photon sends your photons. The photons are propagating, they are detected, and the detectors are sending back electric signals to the computer, to the FPGA, and then it goes back to the user and is plotted on the screen. So the hardware, in the heart of the hardware, we have a quantum photonic chip. So this is a concept. So it's drawn in PowerPoint, let's say. And there you have different stages on the photonic integrated circuit. So it's a network of waveguides, splitters, interferometers, and so on. And then you realize single photons, you generate single photons, and you generate, for one idea we have through nonlinear four-wave mixing, you generate two new photons at two different wavelengths with respect to the optical pump, and these photons are your entangled states, photons, and they are so-called qubits. And then they can be manipulated, make interfere, and then you read out the output of your waveguide. So these photons go into detectors, and the detectors click at the arrival of a single photon. Okay, so they are very sensitive devices. When a single photon comes, you realize, and it's an avalanche diode, it realizes a huge burst of reverse current, and then you detect, let's say, the event of photoabsorption. This is what we have right now as, let's say, as this device you can see here. So here there is an analog chip schematically shown here that is controlling all the electric signals that are needed to reconfigure your integrated circuit. You remember I was talking about phase shifters that can change the amount of light that passes from one waveguide to the other through the coupler. So these phase shifters are controlled externally. So this analog chip receives signals from your computer and then sends currents to micro resistors over here, and it changes the system reconfiguration. So you have one system, but this system can be reconfigured like to allow the light to go in one direction or the other direction or whatever. So you have reconfigured it. So this is what we have now. It's a 2 centimeter long and 5 millimeter tall silicon chip with silicon nitride waveguides over there. The waveguides actually are very difficult to see, but you will see in another picture later on. What you see here as lines, these are electrical lines. Okay, so these are aluminum lines on the micro fabricated, nano-fabricated chip. And then, so we call it quantum photonic integrated circuit. So this is the chip that actually has all the waveguides and integrated detectors in this region. But then you need electronic control, the analog chips on all the sides of the central chip. So these are called ASIC chips, and this is application-specific integrated circuit. And PWM stands for pulse width modulation. So it's a way of sending electrical signals to the paths of the electrical connections of the chip, from this chip to the other. And then, so there are 4 of them. And then at the end, outside of, close to the detectors that are on the photonic chip, outside you have another specific chip that is called gator. So this gator is allowing to detect one photon, and after detection, bring the single photon detector to a normal state where it can accept another photon. Okay, I will, for the time we have, I cannot explain very well what is happening, But if you remember from breakdown of a reverse diode, electronic diode, at some point you have the saturation current, and the saturation current goes into breakdown, strong electrical current passes. So when the photon is detected, you go into a breakdown. Let me see if I can draw even. Maybe I can draw. So, okay, I hope. So this is a, what it is. Okay, so you have a diode characteristic, which is typically something like this, and then you have a strong breakdown. So your single photon detector is set to work at this point in a way that when a photon comes into your device and it is absorbed, it generates a very tiny photocurrent, and then you jump into this state. Okay, so the current slightly, the voltage increases, and then you go into very strong burst of current. But then when the next photon comes, you cannot detect it unless this is not canceled, this situation, and you are brought back, let's say, to this situation and wait for the other photon. So this is essentially what the gator is doing. Okay. Oh. Wait a while, because now I have to understand how I have to remove. Okay, I have the eraser. Oh, okay, great. Okay. Okay. Now, this is an image to show how the phase shifters are working, so the reconfigurability. So you can recognize this is what we have here. It's the thermal image of this device, which is, by the way, mounted on a PCB board. Of course, because to the PCB board, we need to connect it to the computer. So at this time, the electronic chips are ready to send signals, and they are going to send signals to tiny micro resistors on the chip. And in briefly, I will show you a large image of that, like this one. This is, for example, a very large zoom of a tiny part here on the chip. Okay, so you have your waveguides. They come. So this is a top image of the chip. You have a multimode interference filter. There is an aluminum line going over the chip. But then this waveguide actually continues, it splits again, and then moves ahead here as two splits. So this is a standard interferometer, this one, okay? What happens that when we send electrical current through this circuit, so this red is not the waveguide, but it is a tiny metal on top of the waveguide, and then the current passes through this arm and then through the resistor, and then goes to the other part of the electrode. So since this resistor is very, very narrow, it's 2 micron wide, there is a Joule heat release in this region. When the Joule heat is released, it warms up also your waveguide, and the waveguide changes the refractive index. Or in other words, you change the phase of your propagating light, okay? And with different powers you send through the power of the heating, of course, the current and the resistivity you should consider of this tiny phase shifter, they are changing the transmission of your signal and the interference of the two arms you get here. So that's why you see that you can change the interference from maximum to minimum, so it's a 1 pi shift of the phase. Or here, you can see it can be done much easier if you create these black regions around your waveguide. These are actually very deep trenches etched into silicon. So these are holes, actually. And these holes do the following job. So they are, of course, holes, and they are containing air. And because of the thermal isolation, because air is not conducting heat, the effect of the heat is much larger, and it does not disperse. The dispersion of heat is not very strong. And then you are more efficient. With lower power, you can get the pi shift with respect to a device which has no these trenches. Okay. Now you will see when we switch on the signals from this ASIC chip, you can notice that several bright spots appear. The thermal camera is seeing, so each of the spots is one of these devices, okay, a double of these devices. So you see different Mach-Zehnder interferometers that are switched, and the current is passing and is locally hitting each Mach-Zehnder interferometer. So you can control the different ones on the same chip and so on. So this is allowing you, or you can run all together and you control your photonic integrated circuit in a given state, okay? So you can, let's say, reconfigure all the chip with different currents and keep it steady there, so the chip has a certain propagation it can provide, of propagation of light. Or you can change the reconfiguration and the light will go in one way or the other way. So here is a video. You can see, this is a top image. You can see the light is coming here from one of the waveguides. It goes to the multimode interference filter. So the light is coming from here, goes there, okay, and then it splits into the two arms of the Mach-Zehnder interferometer, then into another multi-mode interference filter, and then splits again. Now, when you run the current, you can tune the amount of light that, due to the interference here, you can create here and the other arm. Let me see if I can run this stuff. Okay, I can run. So please pay attention on what is happening here. You are changing the current that goes through the electrical lines, which are these white lines, and they are creating a heating in these two regions, okay? And this heating, depending on how you are balancing the heating, can allow the light to split totally in one or split totally into the other. I hope this is explaining a bit what is happening. Now then, the last part is the detection of your single photons. So schematically in this region, what you have that your waveguide, which is this one, is going down and sitting on the photodetector, which is on the in the substrate, okay? So you have, in most of your optical chip, you have the waveguide, which is very far, so this is a cross-section, which is very far from the silicon substrate, because silicon substrate otherwise will absorb the light from your optical mode here. So it is far enough because of the very thick optical cladding, so it's an isolating SiO2 material. But at some point, the idea is to bring this waveguide and to make it sit on the silicon device, which is a photodetector. So what happens that when the light reaches here, it immediately goes into the silicon, refracts into silicon, because silicon has a much higher refractive index with respect to silicon nitride, which has an index of 2, and this one is 3.4, 3.5. And when the photon goes there, it is strongly absorbed because it's a photon at 800 nanometers, and silicon is strongly absorbing there. And the photon is generating a photocurrent. So you create an electron-hole pair, and they are separated then, and through this metal contact and the back contact on the substrate. And you are generating, let's say, a burst in the single photon avalanche diode that is situated here. Okay, so this is what is the optical simulation showing. So in the first part of the circuit, it is totally isolated from the substrate. Then it slowly goes down. And when it sits on silicon, you see that the light is refracted totally into silicon. And this is going to be absorbed. So if the detector, if this region is very long, at the end of the waveguide, you will not have any light and everything will be completely absorbed by silicon. Okay, so this is the schematic showing that at some point we need to make this coupling, but I wanted to show how this form of the waveguide can be created, because this has to be extremely smooth, and with normal etching methods, which are dry plasma etching methods in microfabrication, you will create a very rough surface here on in the SiO2 layer. So this is the cladding. And if this is very rough and your waveguide then is deposited on top, the single photon will be scattered out and lost before it reaches the detector. So this part has to be very, very smooth. And the smooth surfaces, typically in technology, in microtechnology, are created when you realize, let's say, chemical wet etching of a material. Because dry etching is a bombardment with ions, which have very high radio frequency plasma energy, and you create a lot of roughness on the surface. Wet etching is very smooth because it's at atomic level reacting with your material and is removing. The problem is that realizing a triangular shape in normal microtechnology with wet etching is impossible, because wet etching is an isotropic etching. Probably you know from your studies at the university, or if you don't know, just to say that if you etch a material, an amorphous material within putting it into a acid, for example, it will etch the same way. You will dissolve your material in all directions in the same way, and that will create a circular profile. Okay, so the etching. So here is a protective mask, and this is where you have your acid, for example, and you want to etch your dielectric film. So when the dielectric film starts to etch, it etches in all directions, and at the edge it will start to create a circular pattern. Okay, and this is not.
Sorry. Can I? So I think the guys are, maybe there are some students, they are not aware what etching is. So etching is kind of removal of the material that you need to shape somehow. Maybe you can just.
Okay, of course, I will do so. Etching in general is removing part of your material. Okay, masking with something to protect it, and removing something that is not protected. So you can remove your material in different ways, like digging it with a very aggressive mode, for example, by bombarding with a plasma of ions like argon or other chemical gases that not only chemically react with your film, for example, this one, but they also mechanically bombard. So what happens that you have like if you put metal inside a corrosive acid, okay, your metal will start to corrode and dissolve. So this is etching, and this is in an acid, in a liquid, it is chemical etching. So it is reacting of the liquid with your material, and layer by layer it is removing your material. So this is isotropic etching called, and it goes in all directions in the same velocity, dissolving your material. While anisotropic etching is something that is very directional, and it is bombarding your material. Okay, and that is also creating a very rough surface of your unprotected part of your material. So in order to make this type of structure very smooth, we want to make a wet chemical etching. So that means in a liquid ambient we want to etch. And that is creating a very smooth surface. I hope this is clear somehow. Unfortunately, it requires another lecture, but I hope you understand that wet etching is chemically dissolving or corroding your material. And that chemical etching, even if it creates very smooth, let's say, profile in your material, this is where the material is gone, okay? So it's dissolved, and this is the material that is still remaining. It creates circular profile. And the circular profile is not good, because if you put then your waveguide here on top of this, it will be very abruptly changing the profile, and you will have a lot of scattering of light, and that is not good. But when you have a possibility to also, let's say, remove your resist little by little, like peeling off from the substrate, the etchant is penetrating underneath, and it because of capillary phenomena, and it is etching also starting from the underneath the photoresist. So maybe I will explain what is happening here. So this is a sonic boom, and I saw that on the YSO chapter you had also some post months ago about Cherenkov radiation, and it is exactly the same thing. When a supersonic jet, an object that is releasing sonic circular waves, is moving, at some point it can move faster than the propagation velocity of sound. When it goes over, what you have that you have the circular, let's say, profiles of the sonic the sonic waves that start to let's say sit one over the other because of the so at this point the circle is small because it's just released. The other one is already propagating when the plane was here, and then the tangent of all these circles that sit on with the center on the same line, the line of the object's motion, you will create a cone. So this is the cone that you see or you have seen in pictures of supersonic jets. So it's the Mach, the so-called Mach angle for different different ratios of the jet velocity with respect to the velocity of the sound. Okay, so this is the sonic boom phenomenon. The same thing is happening formally. Is happening the same thing when the liquid, your acid, is penetrating under. So it is creating, let's say, circular shaped etching at each new point. And all these circles, you can see how similar they are. They are sitting on the same line. And this same line, if you etch very long, they will create a very triangular shape of your surface. And this is in a cross-sectional image. You can see the this cladding material of oxide, how flat it is etched. So this is a real cross-sectional image. And you can see also that you have a very low angle, let's say, wedge structure. You can see from a photo from top. And these colors, if you remember or guess, are those that are called Newton rings. So Newton rings is what you see when a droplet of oil or petroleum is benzene is in the rainy asphalt. Is you can see these shapes. These shapes are saying simply that there is a thinner layer of your oil, thicker, and the more dense and close they become, these colors means that the thicker is your oil film here with respect to the edge. And this is just showing that the material underneath here is becoming thicker and thicker, and then this is your waveguide that is at this region, and then it starts to go down to here. Okay, so this is the descent, and it's exactly what you see here in the lateral view. Okay, so this is an image that kind of video that shows how we create the electronic spud device. So these are the dopings of different levels, N doping, P doping, and so on in silicon. Then we create the stadium shape, and then we create the waveguide that at some points from here, you see this stadium, the waveguide goes down over the wedge shape. Then we put metal, then we contact with the metal the spud device that is like 2-3 microns underneath this level, and it is in the substrate. And this is the final situation we have in the end of the process. So this level is at least 2-3 microns closer to us than this level. It is deeper in the substrate. So here the waveguide goes down, sits flat on the doped regions under there where the spud device is. The spud is the detector, and then it rises up again and then goes flat. So the idea is that the photon comes without any losses in the waveguide. It goes down, descends, and sits on the nitride, sits on the silicon, and it is absorbed here completely by silicon, and no light is remaining in the waveguide. and then it clicks, and then this contact from the spot and the back contact of the on the wafer, they collect the electrical signal from your device. Very last part about the photon sources. I will be very fast here. So the photon sources we try to develop, and we continue developing is based on 4 wave mixing. You probably will remember these things given by Stefano Signorini and Massimo Borghi. So I will not probably go too much in detail about this. The ring resonator allows to generate absorbing 2 pump photons. It generates, 1 pump photon, 2 pump photon they generate here. It generates 2 other photons at 2 different signal and idler wave vectors and energies. And you have to conserve the energy, you have to conserve the momentum, so your process is efficient. But actually what happens that the resonator is providing with several modes, and these are the several modes of the same resonator coming with different azimuthal mode numbers. But what you need that when you generate the photons, so you pump at 1 pump resonance, because you have to be resonant here so that your light goes into the ring. And then when it absorbs, you want that your photons come out exactly on 2 other resonances. You need to assure that the energy distance between the modes is constant. Otherwise, if you have dispersion and this distance is changing in frequency, you will get that the signal and idler photons are not exactly sitting in the resonant, and you will have very, very inefficient generation and collection of new photons. So when you realize, let's say, dispersion engineering of your waveguide by the geometry of the waveguide or the composed materials of the waveguide or the surrounding, you will be able to generate, let's say, dispersion-free or 0 dispersion or anomalous dispersion regions for a good, let's say, nonlinear generating device. And we did some research also with material that is very similar to silicon nitride. We did the group velocity dispersion studies to understand where we could expect to have 0 dispersion, so that the free spectral range, so the separation of different resonances of a ring are constant, so you generate efficiently. We noticed that if we make the system with covered oxide on top of your ring resonator, so this is the waveguide of the ring resonator, so your dispersion is not good, and you would like to have a 0 dispersion at some point, and then by removing the top layer on top of the ring, we can tune it perfectly, and then you can see that in these devices, which are the dark, the full line curves here, you can have, let's say, the flat situations for the free spectral range. So the free spectral range here is very constant and is not changing with it. A spectral range in another device, it can be in another place, but eventually this is what we call the dispersion engineering. So eventually from top, this would be technically looking like this. You have a waveguide covered with another oxide on top, but around the ring you remove, let's say, all the oxides. So the ring here has this form, or let's say this is the coupler, this is the ring. So exactly in this region. So when you have air there, your ring is engineered for nonlinear generation. And then we can have also a micro resistor, like you saw it before, to tune the resonances of the ring resonator. And this is an actual photo of the optical image of the chips fabricated. And right now we are also measuring them with the colleagues at the University of Trento in the Professor Pavles's group. Okay, so final things. This is, for example, the layout of the circuit of one of those chips you saw bonded with ASIC chips you saw, and this is how we design. And then what is when you realize, so this is a real optical image, and this is a real optical image of the 6-inch wafer. So this is 15 centimeters in diameter. You can see many devices. This is one of the devices shown here, and this is 2 centimeters by 5 millimeters. And you can realize in one shot many wafers, and because you can induce some variations if you want to see the process variations can lead to something more interesting things, study them, and so on. And some final images. This one you already saw. This is an optical image of the waveguide, of the Mach-Zehnder interferometer. We see the trenches here. The trenches are the deep etchings, and you see that the metal lines bring the phase shifters on top of the waveguide here, and there are different waveguides, different heaters, and they are all electronically controlled by external pads. And this is the edge of the chip where we have the detectors, these detectors, okay? These detectors, for each waveguide, you have one single spot, and this is that spot, for example, this is the 4, and this is the 4, and then this stuff is zoomed here, and you can see how it looks like actually. And yeah, of course, I thank you very much, and thanks for your patience. I hope it was interesting and it was not boring, because I talked probably, I don't know, 1.5 hours. And yeah, of course, I have to thank to all my colleagues and collaborators over these 22 years. And you can imagine that there are many people, and I cannot one by one write everyone's name there. And of course, this is a group work, and if without a group collaboration and teamwork, this stuff cannot be realized never. And yeah, last thing, that we will have new openings in 2025 for young researchers positions that you can mail to me, or you can check from time to time on this web page, because we post, and also on LinkedIn I will post probably some new openings that are more related to integrated optics. So thank you very much.
So